So we continue with our polar coordinates. And there's a lot to look at with these polar coordinates. And your calculator is more helpful than I thought it would be. I apologize for that. I'm going to use the one on my phone, so it's going to look slightly different, my pictures, but you can work with it with yours. But in order to sketch a graph, what you're going to do is to create your R and your theta column and then graph. And generally, you're going to go from 0 to pi at least. You might go from 0 to 2 pi. So this next problem says sketch the curve of R equals 1 plus sine theta. So we're going to pick our theta and find our R. So theta is 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3. All of your special triangle values, all of your special angle values, and then in the second quadrant, 3 pi over 4, 5 pi over 6, and then pi. You could keep going. You probably should. As we keep going, we find that we have 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, 11 pi over 6, and then 2 pi. So we're looking at 1 plus sine theta. Now 1 plus sine theta, it shifted up 1, so instead of being between 1 and negative 1, it's between 0 and 1, and your sine graph looks like this. So that helps some people draw it because they know that it works like that. Let's fill in our triangle here. Let's fill in our chart. Sine of theta, if you have pi over 3 and pi over 6. Pi over 4 is easy because it's square root of 2 over 2. You have square root of 3 here, 2 and 1. So sine of 0 is 0 plus 1 is 1. So I know I'm filling the chart in backwards, but that makes it easier to graph. So the sine of pi over 6 is 1/2 plus 1 is 3/2. The sine of pi over 4 is the square root of 2 over 2 plus 1. Now I know that this is 0.71, so it's 1.71, which is probably more helpful when we graph. So pi over 3 is the square root of 3 over 2, plus 1 is 1.866. I should check that number. The sine of pi over 2 is 1 plus 1 is 2. Now sine is positive in the first quadrant, so this would be 1.66. In the second quadrant as well. This will be 1.71. This will be 1.5. And then at pi, sine would be 0, so that's 1. And then we continue. 7 pi over 6 will be, the sine of that is 1/2, but it's negative because we're in the third quadrant. Plus 1 is 0.5. And then we have 1 minus 0.71, which is 0.29. So then we have 1 minus 0.866, and it's 0.134. And the sine of 3 pi over 2 is 1, and 1 plus negative 1 is 0. Oh, that's why I'm saying minus, because it's 1 plus a negative. This will be 0.134. This will be 0.29. This will be 0.5. And then we're back at 1. Everything has a radius 2 or less, so I brought it in big so we could look at it. So we have a radius of 1 and a theta of 0. So that means that it goes right here. Pi over 6 is this one. This is pi over 6. And this one we're going to call pi over 3 and pi over 4. It may be closer. this would be better if it was labeled better, but that's okay. And then we have a radius of 1.5 for pi over 6, so that'll go here. And at pi over 4, we're at 1.71. And at pi over 3, we're at 1.866. And at pi over 2, we're at 2. And then we're back to 1 point. This is our 2 pi over 3. And this is 3 pi over 4. And this is 5 pi over 6. So at 2 pi over 3, we're back at 1.866. And then 1.71. And then 1.5. And then we're back to 1. And then we say 0.5 at 7 pi over 6 and 0.29 and then 0.1, and then we hit the 0, and then we come back out to the 0.13 and the 0.29 and the 0.5, and then we're back to 1. So it doesn't start at the point I started at. It's just easier to draw it this way. So it comes and it loops around like such. And this shape is called a cardioid because it's shaped like a heart. A cardioid. Because it's shaped like a heart. So your sine graphs tend to have a cardioid in them. And let's look at another graph. Before we do, this is what you can do on your calculator. So you tell your calculator R equals 1 plus sine theta. Your xt theta n, when you push that button, it's going to give you a theta. And you'll see the cardioid happening. You can tell that's a little prettier than the one that I drew, but it's the same. So with today's technology, you could use your calculator to help you. The next problem says to sketch R equals cosine of 2 theta. So cosine of 2 theta, that tells me I have a period of pi, so I only have to go to pi. So I'm going to list my thetas on the right. So we have 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, 2 pi. So cosine of 0 is 1. Sorry about that delay there. I need to build a triangle. You either memorize the unit circle or you learn triangles. For those of you who do triangles with me, this is for you. For those of you who memorize the unit circle, go for it. So the cosine of pi over 6 is adjacent over hypotenuse. So the cosine of 2 pi over 6 means that we are in the 2 pi over 6 reduces to pi over 3, and the cosine is 1/2. Pi over 4 times 2 is 2 pi over 4, which is 1/2. So pi over 2. Cosine of pi over 2 is 0. Pi over 3 times 2 puts us into the second quadrant, so we're going to have a negative value. So cosine of pi over 3 is 1/2 negative in the second quadrant. Pi over 2 times 2 is pi, and cosine of pi is -1. Cosine of 4 pi over 3 is in the third quadrant, and it's -1/2. Cosine of 3 pi over 4, when you multiply by 2, it becomes 6 pi over 4, which is 3 pi over 2, and the cosine of that is 0. Cosine of 10 pi over 6 is 5 pi over 3, fourth quadrant, +1/2. And cosine of 4 pi is 1. So now we can look at this graph. Let me get rid of the triangle and bring in the graph. So when we have a radius of 1, we have a theta of 0. At pi over 6, we have a radius of 1/2. At pi over 4, we have a radius of 0. So then when our radius is -1/2, we're at pi over 3. So here's our pi over 3 line, and -1/2 means I come down here to the negative side of that line. There's -1/2. Now, it's going to be important that I know which way I went, so I'm going to kind of fill this in as I go, only because I know what's happening. When I get to pi over 2, we're at -1, so this is pi over 2, and remember, a negative radius pops on the other side of the origin, and then 2 pi over 3 has a radius of -1/2 again, and then we're back to 3 pi over 4 is 0. Then 5 pi over 6 is +1/2, right here. And 2 pi is 1. And we're not back at the origin, so we have to keep going. So sorry, this would be pi. But pi times 2 is 2 pi, which is still 1. So now we need to keep going on our Cartesian, on our list of points. We need 7 pi over 6, which gives me 7 pi over 3, which is +1/2. So 7 pi over 6 is here. It's this line just passed, but we're moving in that direction. And then we would have 3 pi over 2. Sorry, that's not the next one. 7 pi over 6, and then we have 5 pi over 4. We're in the third quadrant, and I've lost it. 5 pi over 4 times 2 is 10 pi over 4, which reduces to 5 pi over 4 times 2 would be 10 pi over 4, which is 5 pi over 2. And the cosine of that is 0. So we're back to 0. So let's draw that loop so we don't lose it. And then as we fill points in, let me tell you, this one is 1/2. Let me keep going. So we have we left off with 5 pi over 4. So the 1/3 quadrant, pi over 3, is 4 pi over 3. And then we have 3 pi over 2. And we have 5 pi over 3. And 7 pi over 4. And 11 pi over 6. And 2 pi. So cosine of 8 pi over 3 would be -1/2. And cosine of 3 pi over 2 times 2 is 3 pi. And cosine of 3 pi is -1. And cosine of 10 pi over 3 is -1/2. And cosine of 14 pi over 4 is 7 pi over 2 is 0. And cosine of 11 pi over 6 is 1/2. And cosine of 2 pi is 1. So let's go back to this 4 pi over 3. Down here is 4 pi over 3. And it has a radius of -1/2, so it goes there. And then we have 3 pi over 2. And it has a radius of -1. And then 5 pi over 3 has a radius of -1/2. This one should be a little higher. So we continue our loop this way. And then 11 pi over 6 has a radius of 1/2. And we have a flower here. So this is called a 4-leaved rose. It's a rose with 4 leaves. So we have a 4-leaved rose. Now we find that our sines and cosines give us interesting graphs every single time. And you can look at that last one on your calculator. There's a couple I really want to show you. Let me do that before we do the slope of the tangent line. We can sketch simple polar curves by hand, but we need a graphing calculator or computer when we're looking at these graphs here for like figures 16, 17, and 18. Do you remember the spirograph when you were a kid? That's what these always make me think of. And you can see the equations for them down below. And they're great, great graphs. So it says some graphing devices have commands that enable us to graph polar curves directly. With other machines, we need to convert them to parametric equations first. So if that's the case, then you let r equal f of theta and write it as parametric equations. Then the parameter tends to be theta. But we're not going to focus on that. An example of that would be r equals, let's look at one. It says r equals sine of 8 theta over 5. That's a 5. So if your calculator didn't have polar coordinates, you would say x equals r cosine theta and y equals r sine theta. Now before we get into that, let's look at the fact that we have sine of 8 over 5, and technically we have theta plus 2 pi n, where n is an integer, because we have all the coterminal angles that go with it. Let me tie it in over here. If we were to keep going on this, we know we started over here. This was our initial point and our terminal point, and we went this way. So we could keep doing it over and over and over again, and we don't have to stop at 2 pi. We could go to 12 pi. We could go to 45 pi. We could keep going, and we're going to keep getting the same four-leaved rows. So that's why we're looking at it in terms of 2 pi n. So then we have sine. Let's distribute. We have 8 theta over 5 plus 16 pi n over 5. So how many complete rotations do we need before we start to repeat itself? So if we look at this, this tells us that it has to be even multiples of pi, because it has to be like 2 pi or 3 pi. So this first happens when n equals 5. So if you think about that, 16 is not divisible by 5. So the first repeat happens at, I don't know that you want to call it repeat. The first rotation would be about n equals 5. Or n equals 10. N equals 5. So we'll probably graph the entire curve if we stay between 0 and 10 pi for theta. So let's let theta between 0 and 10 pi. So before we would have had x equals r, which is sine of 8 theta over 5 times cosine of theta. But now we can put it in terms of t, sine of 8t over 5, cosine of t. And we can do the same for y. Y is r, which is sine of 8t over 5, and then sine of t. Now, you can't put those together. You have to leave it like that. But t is between 0 and 2 pi. So you can use what we learned earlier in the chapter and look at the parametric equation, and you'll find the same curve. Notice that this is a rows, and it has 16 loops. That's an interesting tie-in to this fact. It's a rows with 16 loops. If you graph this on your calculator, it gets very messy, but in order to see the whole thing, you're going to need to set your window, your theta max at 16 pi, 20 pi, somewhere in there. Then you could zoom in and look at it. So, interesting fact. All right, let's do a little more with the graphs. This is the graph that we just talked about. If you use your graphing calculator and you say r equals sine of 8 theta over 5, it'll actually look like r equals sine of 8 theta over 5. This is the graph that you come up with here. So it's a pretty graph. If you zoom in, you can see it nicely. Let's look at this. The problem says investigate r equals 1 plus c sine theta. So play with values of c and look at how it shapes, how the shape changes. The curves are called limacons. There's an accent under the C, and it's after the French word for snail because the shape of the curves for certain values of C. So this is what we see. See these loops in there? And then this is we looked at the cardioid earlier. So we have a cardioid here because it looks like a heart, and some of them look like upside down hearts. But as your C gets smaller, notice that when we approach C equals 0, here we have a circle, and then it flips over, and your cardioid is upside down, and then you're back to the loop in it. The limacon is shaped like an oval. The oval becomes more circular when we look at C equals 0. So down here it tells you limacons arise in the study of planetary motion, in particular, the trajectory of Mars, as viewed from the planet Earth, has been modeled by a limacon with a loop, as in parts of Figure 19, with the absolute value of C is greater than 1. So that means the 2 here on the top corner and the last one down here in the bottom corner. So what we have left now is the slope of the tangent line. And in order to do that, we need to talk about the derivative because that's where the slope comes from. So we know x equals r cosine theta, and our r is our f of theta, cosine theta. So we could be using either of those. And y equals r sine theta, which could also be called f of theta sine theta. Now dy over dx is very much like it was in parametrics. We're going to have the derivative of y with respect to theta over the derivative of x with respect to theta. Now this is a product rule. Pay attention to that because we have a theta and an r. So let's look at these two. Now the derivative of y, I like to keep the r and take the derivative of sine, but if you look it up in your book, they're going to do it the other way. So let's take the derivative of r to be the derivative of r with respect to theta. We don't know what that is. And then we keep the sine theta, because it's product rule, plus we keep the r, and the derivative of sine theta is cosine theta. Now we're going to do similarly on the bottom. The derivative of r is dr over d theta, implicit differentiation, and we keep cosine theta, plus we keep the r, and the derivative of cosine theta is negative sine theta. So let's change this to a minus r sine theta. So that would be our derivative of y with respect to x. So I'm not big on memorizing things. I think if you know this equals this fraction, you can come up with these, but this is what it really is. So this last craziness is dy over dx when you're in polar coordinates. Now, we have an example that says, for the cardioid r equals 1 plus sine theta, find the slope of the tangent line when theta equals pi over 3. So we're going to say dy over dx equals, and let's look at the top. So we have it in front of us. Let's go ahead and use it. dr over dr with respect to theta. So the derivative of r, the derivative of this r with respect to theta. So the derivative of 1 is nothing, and the derivative of sine of theta is cosine of theta. And we keep the sine theta here. Plus r is 1 plus sine theta times cosine theta. And then the denominator, the derivative of r with respect to theta is cosine of theta times cosine of theta, minus r is 1 plus sine theta, and then we have sine theta in the formula. So let's simplify this. So we have cosine theta sine theta plus cosine theta plus cosine theta sine theta. Now in the denominator we have cosine squared theta minus sine theta. Don't forget to distribute the negative. Minus sine squared theta. So we're looking at pi over 3. The cosine of pi over 3 is 1/2, and the sine is the square root of 3 over 2, plus cosine is 1/2, plus 1/2 times the square root of 3 over 2. Now 1/2 squared is 1/4, minus sine is square root of 3 over 2, minus sine squared is 3 over 4. So we can simplify the top and the bottom separately. So we have the square root of 3 over 4 plus, this is 1/2, but let's make it 2 over 4. So we have common denominators, plus the square root of 3 over 4. And in the denominator, we have 1/4 minus 2 square root of 3 over 4 to get common denominators, minus 3 over 4. By the way, if we were looking for an answer for the second derivative here, or for the derivative, we would combine and get like terms, because this would be 2 cosine theta sine theta. And the denominator doesn't really change. We just have cosine squared minus sine theta minus sine squared theta. So just know that if you're looking for your derivative, it would need to be simplified more. But we're plugging it in. So the top fraction is 2 plus 2 square root of 3 all over 4. And the bottom fraction is 1 minus 3 is negative 2 minus 2 square root of 3 over 4. So we're going to divide fractions. We have 2 plus 2 square root of 3 over 4 times 4. Let's factor out a negative 1, and we have 2 plus 2 square root of 3. Now, if you look carefully, these fractions cancel. The parentheses cancel because they match exactly. The 4's cancel, and we get negative 1 for our slope. Isn't that a great slope? So our slope is negative 1, and that's what they asked us to find. The second part says find the slopes where the tangent line is horizontal or vertical. So for a horizontal tangent line, that means that dy over the derivative of y with the numerator, the derivative of y with respect to theta would be 0. So this is our horizontal. And then for our vertical, we would say that the derivative of x with respect to theta is 0. So let's look at least the top. We have 2 cosine theta sine theta plus cosine theta. So we would say 2 cosine theta sine theta plus cosine theta equals 0. So we factor out a cosine theta, and we have 2 sine theta plus 1 equals 0. So cosine theta equals 0, and 2 sine theta plus 1 equals 0. So sine theta equals negative 1/2. So our reference angle is pi over 6, and we're in quadrants 3 and 4 for sine to be negative. So that means theta is 7 pi over 6, and 11 pi over 6. And then cosine of theta equals 0 at pi over 2 and 3 pi over 2. Now, in order to find where it's vertical, you would set the denominator equal to 0. And I think you've got all you need to do this lesson. I might do another video with some of the examples from the lesson. Thank you. Have a great day.